Okay, I think we can start. Good morning, all the participants of the summer program on 3D printing, manufacturing and infrastructure. Now we are into the fourth and final of this program. So during the past third weeks, we had mix of lectures from industry and also by our internal faculty. I hope the participants enjoyed these sessions because the speakers were from a different background, like polymer 3D printing, metal 3D printing, 3D printing of civil structures, 3D printing of composites, the CAD modeling part, the hardware of the 3D printer. So we begin this week by an exciting talk on industrial 3D printing. I welcome Mr. Sachin Kadam for this session. So he represents VOXELJET India. I think he will definitely introduce the company. Just very briefly, I just read a little bit that it is a German company which has started its operations in December 2015 in India. The company is headed by Mr. Shah, who is managing director of the company. And I also read one news that they installed a big industrial printer at a foundry company, that is PK Castings. So I welcome Mr. Sachin to this session. Thank you, Sachin, for accepting our invite and sparing time from your busy schedule for our event. Much. So now, please take over the session.
Good morning, guys. So I'm Sachin Kadam, working for VOXELJET India, and I work as a senior manager, technical services. So my profile is basically installing these 3D printers, project execution and commissioning of these 3D printers. So today we'll discuss about the 3D printing technology and the industrial 3D printers from VOXELJET. So we'll discuss today about company. I'll give a brief description about the company, the processes we use for different castings and different materials. We discuss different materials also, different systems we have for different applications. The services we provide to the customer who don't have 3D printing machines and they wanted to get our services, 3D printed parts. So we print the parts for them and deliver it to them. And also we discuss few interesting case studies from different customers. And then, so we are a 3D printing company founded in 1999. It started with 8 people. Now we have more than 250 people in our company. The headquarters in Augsburg, Germany. We also have subsidiaries in Detroit, USA, in London, UK. We have office in Pune, in India, and in Shanghai, in China. So as Doctor said, we have installed one big machine, but it is not PK Steel. It is in Kirloskar Brothers Limited. We have that's the biggest machine we have in India, and that's the biggest machine in the world. So the scope of business, we manufacture state-of-the-art industrial 3D printers, and the company is listed on NYSE stock exchange. So VOXELJET Technology. So VOXELJET 3D printers are use binder jetting technology. So where we use the powder as a base material, and with the print head we jet the binders as a hardening material, and all the process takes place at the room temperature. And we have, as I said, we have the largest 3D printer in the market. So we can build a large volume of 3D printed parts. The biggest 3D printer is of size 4 meter into 2 meter into 1 meter. So it can build of 8,000 liters of volume. So the productivity is high. The advantage of 3D printers is the printed parts are highly accurate. The tolerances are very less. The accuracy is around point 0.2 to 0.4%. And the the details of the part are really great. So, and also we have attractive material sets for different type of applications and for commercial applications. So, so the printing process. So, last couple of weeks, you all guys have heard a lot of about 3D printing technologies. So the principle is basically same of all the 3D printers. So you need a CAD data first of a part, and then it is fed to the machine. The machine has a nesting software where you can slice it, slice the CAD data of 150 micron layer or 300 micron layer, depending on what kind of process you are using. Uh, so the CAD data is sliced, and then on the machine, the powder is recoated with the recoater, and then after recoating, the print head prints the data on the platform as per the layer data provided by the machine computer. And these steps are repeated until the parts get finished. So after the parts are finished, normally the job box is removed, and there is unpacking station. We have to unpack the parts, clean the parts, and the parts are ready for further process. So I have few short videos to show you how the process works. So I'll just play it.
VOXELJET presents the chemical 3D printing process, powder binder jetting. The 3D printing process runs on all available VOXELJET printing systems with a variety of different particle materials, such as sand, plastics, or freely selectable powder materials. The only requirement is CAD data of the part. The process starts with the application of the part to the building platform by a recoater. Afterwards, the print head applies the binder selectively at the areas where the future part is to be produced, thus connecting the layers. After the binder has been applied, the building platform is lowered by the layer thickness. This process is repeated until the part is completely finished. The unprinted particle material is removed after the printing process. The models can be used directly for metal casting or as design and functional models without time-consuming post-processing. Find out how VOXELJET can optimize your production.
Okay, so we have different processes for 3D printing. One is sand process. So the sand process, we use the green sand or silica sand, and where you can print the molds and cores, the negative of the pattern, and then in a foundry you can do a metal casting from these parts. So we have the largest industrial printer. The build space is, as I said, 4 meter by 2 meter by 1 meter. The resolution is really high, like we print with the 300 dpi resolution, and over 25,000 individually controllable nozzles. Means the printer has small nozzles from where it jets the binder. The binder jetting technology is similar to the printers you have at offices or home, jet printers. So it prints through these nozzles according to the CAD data provided. So basically, like if you have a PDF file of 100 pages and you print that 100 pages on a basic printer, office printer. Similarly here, the CAD data is sliced and it generates the number of pages. It's similar, like of 150 micron layers or 150 micron or 300 micron layers are generated, and it generates 600, 700 layers. It depends on the size of the file, and then it prints layer by layer these data. And the job box is integrated, and then it's also flexible that how big you can print. So it's not like you have to print full 4 meter every time. So there is a flexibility that you can print a smaller size of job box also if you don't have that big volume to print. So this is a sand casting process. The picture is of Francis impeller. This part is printed on a sand casting process. Normally, the Francis impeller with the conventional method, you have to print every fins. You have to produce every fin separately, the core. So the number of molds or cores you create is many, like 15, 20 or something. It depends on the kind of core you're printing, especially for the impellers, and then they join it together in a mold. But here you can print it as a single piece. So after printing printing the cores and molds, they are finished with the coating. So you get the better surface finish, and then they do the casting, and you can take out the finished parts and do the remaining the process, after process, like removing the burrs and every other partning lines or something. So the advantage of 3D printing is no complex core assemblies. So it saves the time of the construction. Post-processing is also simple. It saves your cost if you produce small series of, if you make a small series of productions. And as I said, it improves the tolerances because you print as a single part and not many part for the core. So the other advantage is the design optimization is also possible with this to maximize the strength and minimize the weight of the parts, which is not possible with the conventional methods, or it is very difficult to do with the conventional methods. Also, the complex geometries, it's very difficult with the conventional methods of mold making, which is very easily done with the 3D printing. And the other thing is, if you are doing with the conventional method, you need to store the patterns for the further production. So you need a space to keep all the patterns together. So this can be avoided with the 3D printing technology. So I have a short video of the sand printed part and and also the casting. It is shown in this video.
VOXELJET offers the manufacture of complex molds using 3D printing. The core of a wheel and its undercuts can now be easily produced in one piece. On request, we can take over the production of the sand mold design based on your 3D data. Depending on the application, prototypes and small series can easily be produced in various sand types. The recoater applies sand to the 4-meter-long build space in one layer. At the same time, the printhead starts to selectively dose the resin where the mold will be created. This layer building method allows for the production of complex geometries with undercuts in one piece. After the build process is complete, the mold can be easily unpacked. The handling of the mold in the foundry is the same as with conventional production method. The unbound sand can be easily removed, and the molds are ready for immediate casting. Because of the different delivery periods, you can coordinate the molds to your production. The VOXELJET 3D printing process allows for the cost-effective and time-saving manufacture of your components at a high degree of precision. The Wolfensberger Steel Foundry and VOXELJET manufacture a complex wheel using a combination of traditional mold construction and modern 3D printing. The external shape of the prototype is made in a conventional manner using existing models. No models are built for the core. It is delivered by VOXELJET on a just-in-time basis and is then integrated and processed in line with the normal work process. Assembly involves just one core rather than multiple core segments. The client can choose from suitable sand varieties for the various cast alloys. The cast features the typical foundry properties and can be optimized through the use of cores printed with the 3D method. The cast can be removed from the mold in the usual manner. A smaller number of core flashes and an excellent surface make for quick and cost-effective cleaning of cast parts. The cast part then undergoes the usual quality checks, such as X-rays, color penetration testing, or ultrasound. The result is a complex wheel that impresses with its component accuracy and consistency in form. Are you interested? We would be pleased to assist you.
Okay, so as you seen in the video, like they printed the code from the VOXELJET and they make a mold from the conventional method, and then we'll see the the material we use for sand processing. So normally we use a silica sand for 90-95% of the mold making in industries. So there are different type of sands with a different grain size, and it depends upon how much surface quality you want. You can select the sand. So these are the material we use: GS14, GS19, GS25. All these sands are supplied with by Strobel. We have a tie-up with Strobel, so they supply these sands to the customer also. And with the sand, we have the layer thickness of 300 mm. We get the strength of 220 Newton per centimeter square. So the different sand for different applications. So another process we have is PMMA 3D printing process. PMMA is a polymer material, and it is basically used for investment casting of parts. So in investment casting or PMMA process, normally we use this powder, which is of 80 micron size, very fine powder, and we print the parts. Here in the first picture, it shows the 4 parts connected with the wax rods, and then we do the shell binding with the ceramic coating, and we burn out the PMMA parts, and then we after burnout we make the casting. We pour the molten metal, and after that shell cracking to take out the parts, and the further processing can be done. So I have a short video of this also for the investment casting process.
VOXELJET can manufacture complex plastic parts using a 3D printing process. It consists of a powder-based process that can be used to create investment casting and illustrative models measuring up to 1060 by 600 by 500 millimeters. When your CAD data is received, it is checked and prepared for the process. Geometries can be changed at any time, as this process does not use any tools. The printing process begins when the recoater applies the PMMA powder to the build space in 100 to 150 micrometer layers. At the same time, the printer head selectively doses the binder at the points at which the model is created. The 3D printer's vertical build speed can reach up to 18 millimeters per hour. This layer building method makes it easy to manufacture complex geometries with undercuts in one piece. After the printing process is complete, the models remain in the box for several hours for hardening. Then the plastic part can be unpacked. The unprinted powder, 100% of which can be reused, is removed with an industrial vacuum and compressed air. The molds are characterized by maximum detail accuracy and precision. They reach their final strength in the furnace. For investment casting, the models are briefly immersed in wax to seal and smooth the surface. Design models are infiltrated with epoxy resin for added strength. The models are packaged carefully to ensure safe delivery to the customer. The wax-infiltrated models are processed the same way as wax models. The conventional production of complex components such as wheels is very cumbersome and expensive. VOXELJET's 3D printed plastic models provide a cost-effective way of producing installation-ready cast parts using the investment casting process, as is the case here at stainless steel expert Schmalz & Bickenbach. This wheel has a diameter of 500 millimeters. However, the VOXELJET 3D printers can also produce components up to 1 meter in length and a total volume of 320 liters. The gating and feed system is mounted after inspection. The finishing process is the same as for conventional wax models. The first ceramic coatings are applied manually, while subsequent layers are added by a robot. The plastic models soften at 80 degrees C and shrink, so that tears cannot form in the ceramic shell. Finally, the 3D printed model is burnt out from the casting die in the kiln. The plastic models burn out with virtually no residue. Now the liquid steel, which is around 1600 degrees C, can be poured into the heated casting dies. The castings are removed once the molds have cooled. Once the casting is complete, gating and feeding systems are removed, sharp corners are deburred, and unwanted surface errors are repaired. This process is followed by non-destructive tests and size inspections in accordance with customer specifications. Whether for prototyping, individual piece, or small series manufacture, additive manufacturing can produce highly complex designs and investment casting models within a very short period of time.
Okay, so so video explains a lot of things. So normally after the printed parts, we do wax coating, and because we need to get a good surface finish, and also it avoids the shrinkage of the parts. For the plastic or PMMA process, we use different type of material, the powders, polypore B, polypore C, for different applications. It has different surface finishes and different strengths, and these can be easily burned out at 700 degrees Celsius for the investment casting. So the plastic, normally the layer thickness for the printing is 150 micron, and the resolution is very high, up to 600 dpi. So the next process is HSS, is high-speed sintering process. So it is similar to SLS process, stereo selective laser sintering, and the parts can be used can be used as for the end use. So the process works similarly. It's only thing is here we use ink uh, and and uh, and the IR lamp for the fusion. The surface can be heated up to 100 degrees Celsius for the fusion. So the recoater lays the powder, and the printed jets the ink, and with the IR lamp or the heating system, the fusion takes place. This is a flexible and open source system, so anyone having a different kind of materials they can use on these systems. So I have the video for this also.
Introducing high-speed sintering, the 3D printing process by VOXELJET. High-speed sintering, or HSS, opens up a completely new dimension of functionality and flexibility for our customers. The benefit of our industrial inkjet technology is that it offers highly accurate build rates, consistent layer timing, and efficient build times. HSS is a physical process. It involves depositing a fine layer of loose powder onto a build platform, after which an inkjet printhead selectively deposits an infrared-absorbing fluid directly onto the powder surface where sintering is desired. The build area is then illuminated with infrared light, causing the printed fluid to absorb the energy and fuse the underlying powder. This process is repeated layer by layer until the build is complete. This process offers the user flexibility to individually adapt the process parameters to specific materials. With this process, complex illustrative and functional models are created using different plastic materials such as PA12 or TPU. HSS offers enormous benefits in terms of productivity, flexibility, and applicability of components. Thus, it introduces a huge variety of diverse applications. We can manufacture functional parts, but also test components and prototypes with outstanding properties and quality. We are constantly streamlining our printing processes, allowing the user to benefit from faster prototyping and turnaround times. The HSS process enables the efficient and flexible production of components from different materials. It is particularly suitable for functional components with high demand of resolution and strength. Contact us here at VOXELJET to see how we can optimize your production.
So you have seen with this process we can produce a fabric kind of material also, which is very flexible. It is also possible with this you can different degree of hardness printable with the different ink inputs. Right now we have this process available with the VX200 system, which is the smallest system we have, which is of size of 300 into 200 into 100 mm. So you can print 9 liter of volume. So and the grain size for this process varies from 55 micron to 1 mm. The layer thickness basically is of 80 to 100 micron. Resolution is 360 dpi. Layer time is 20 seconds, and the materials are different materials like PA12, PP, TPU. That is polypropylene material, and it can be used for the directly as a end use parts. So we have different systems for different applications. The biggest system is VX4000. The size is 4 meter by 2 meter by 1 meter, the build size, and it is basically used for sand process. The VX2000 is also basically used for sand process. It has size of 2 meter into 1 meter into 1 meter. The VX1300X, that's a new system. It is still in the development, and it is also basically used for the sand process. VX1000 machine can be used for sand, also for the plastic parts. The size is 1000 into 600 into 500. So it builds around 300 liters of volume. VX500 has a volume of 500 mm into 400 mm into 300 mm. VX1000 and VX500 are the most popular machines among the customers because it gives flexibility for them to print small to large parts. So that's the most popular. And the VX4000 we have in India at Kirloskar Brothers Limited, where they print centrifugal pumps, the big pumps. Some of the castings from KBL varies from 5 tons to 10 tons or maybe sometimes more. So they print pump casings, impellers, and a lot of other pump related parts. So advantages of industrial 3D printing. No design constraints. You can design any kind of complex geometries in this. Also, the design changes are simple. Refinement is also simple. Manufacturing of parts with any complexity is possible. Fast production, like you design the CAD file and just give it to the system, and then it produces the parts. So it's very faster than the conventional methods, because the conventional method takes a lot of time. You need a lot of tools for that, and in this 3D printing, the tooling is not required. Uh, uh, also the gating systems and veins for the molds can be easily optimized, so that there will be no turbulence while pouring the molten metal. Also, there will be no gas will traps inside the molds to have the defects. So that is very easily done with the 3D printing. With the simulation is very simple. Uh, the faster production, because it produces the parts within 24 hours. Even the bigger machine takes maximum 60 hours. So fast production and reduction of product development cycles. Flexibility, tool-less and flexible production, high level of design freedom, and the economic production of prototypes and models. Serial production can be done. So basically it saves a lot of time and money with the 3D printing method. Numerous industrial application like sand molds and cores, manifolds, water jacket cores, formwork for concrete, uh, and the plastic models for uh, arts and architecture designs, for props which are used in films and all. Plastic models for the different different applications. So can we produce automotive parts like manifolds, engine blocks, gearboxes, water jacket cores, mechanical engineering design, gearboxes, impellers, uh, art and architectures, as shown in the picture. You can print the bigger parts into uh, different pieces and join them together and make a huge structure out of it. That is possible. So we will see some case studies from the customers. So this is the engine block produced for the one of the customer. Uh, this is a French car making company. They were producing cars for the Grand Prix or the racing cars, Delage Type S system. The car was 100 more than 100 years old, and the engine was broken down. So with the 3D printing, first they scan the complete engine block, uh, make the CAD module, and then they produce the part with the 3D printing. And the 3D printing was the only option they have, because it was with the cost and the time, uh, and the flexibility of the complex geometries can be print. Uh, Also the optimization of the designs. The 3D printing was the only option they have. With the conventional method, it was not possible. So they just printed the engine blocks with three molds, one core and two molds. With a conventional system, they would have needed more uh, more molds to produce this part. So, as I said, the gating system can be optimized with the 3D printing, so that there will be no gas trapping and the defects in the casted parts. Uh, so this is one of the case studies of the engine block, and they restored this 100-year-old car with the 3D printing technology. So the second case study is for the exhaust manifold, which manufactured for the Brabus. The Brabus is a they they fine tune the cars or to increase the performance of the cars. They fine tune many components from the cars, and there was a challenge, with the fine tunes, they can easily increase the speed and torque of the engine. And we produce different parts for the Brabus with the help of Lutkemeyer. We produce exhaust manifold, turbine housing, and compressor housing with the different materials used. And these parts for this Brabus are produced with the phenolic binding technology. The phenolic binding technology is also sand process, where normally in silica sand you use the furan binder, where the binding takes place at the room temperature, but in phenolic you need to heat the job box at 100 degrees Celsius, and also there will be a IR lamp to heat the surface of the sand for the bonding of the material. So they use the 3D printing technology to again to save the cost and the time. the lead time for this project was just 23 days. With the conventional method, it would have taken months. So the next case studies is Autodesk swing arm. So this is we have a customer TEI in USA. So they make they make a lot of casting parts for the automotive industries. And this swing arm is manufactured for the one of the bike manufacturer. Uh, uh, the the bike manufacturer is Lightning Motorcycle from the USA. They make the racer bikes, and the Autodesk is is a development of they are doing the development of the parts, and they 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 printed the prototype of this swing arm with the 3D printing, uh, because again it gives the flexibility of design, and also with the 3D printing they can increase the strength of the parts, stiffness. They can reduce the weight of the part. So that is why they use the 3D printing technology. You can see here the 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 part with the conventional method and the part printed with the 3D printing technology. So they could easily uh, reduce the weight of the part, and also at the same time they could increase the strength of the part and the stiffness also. So they just produce the three with the 3D printing. We just make three molds. One is scope, drag, and the core. So the drag is the lower portion of the mold, and the cope is the upper portion, and the core fits in between. And then they casted this part. So with this you can maintain the performance of existing swing arm while reducing the weight, geometry's freedom, and the stability of classic precision castings. The next case study is from the man ship cylinder head. So it's from the diesel engine. So here they also wanted to print a prototype, and the lead time that they wanted to produce these parts within 20 days. But with the conventional method, it could have take more than month or something. So they opt for the 3D printing technology, and because these part was having a lot of undercuts, and it was a very complex geometry. So with the conventional method, they might have produced the conventional method required almost 40 to 50 different parts, and for the core, and uh, it was really a complex design. So they prefer 3D printing technology, and the number of parts reduced from so many to, like, here they said 19 to just 2. So we just printed 2 pieces, and with 3D printing, and they casted the successful part. So the lead time for the total project was only 5 days. The build time was 29 hours. And it was a big casting. The weight of the casting was 2.1 ton. So it's a really big casting. So another example of sand casting is again a swing arm for the agricultural uh, uh, agricultural machine. So this Amazon makes agricultural machines, and the the first design was very heavy, and also it has a lot of parts are welded together. So with the 3D printing technology, we optimized it and uh, casted in one piece. So there is no welding of any parts. So if you see the welded parts weighing 245 kg, the welding length, the total welding length was 16.5 meter. And if we compare the casted parts, uh, the casting weight was reduced by 20 kg, almost 10%. And the lifetime, the strength was increased almost 3 times. So the middle one was the first iteration, and the last one was the again optimization of the swing arm. And then after further optimization, the weight of the swing arm got reduced uh, further by 10%, and the lifetime again increase. Yeah, with from the conventional method, it's all again 3 times more. And also the advantage is time to market. So with the 3D printing, it's very fast to produce the parts. Uh, yeah. So this is one of the case study for the agriculture machines. So these are the pictures how they done the casting process. It's a huge part. Uh, so investment casting also, these are the pictures for investment casting parts. Some of the lamp designs are green lamp designs for the LED lightings nowadays we use. So the groove heat sinks are made for LED lights so that the lifetime of the LED lights can be increased. It works as a heat sink, so at the normal room temperature, it can work for a longer time, and obviously it helps improving the lifetime of the LED lights. But the advantage of 3D printing is uh, for the LED light, you can print variety of different designs, and yeah, it gives a good look to the LED lights, and yeah, you can optimize different shapes and size for different type of LEDs. Also some mechanical parts shown here. So the investment next case study is investment casting for aircraft doors. This is only a prototype made for the aircraft doors. So the Soj Claire is manufacturing chairs and aircraft doors and some components for the aerospace industries. So the initial design was of 7.2 kg weight, and with the 3D printed on a VOXELJET, the new design was of 4.8 kg, the weight reduction of 30%. So in aerospace industries, it's very important to reduce the weight of all. They are trying to reduce the weight of many parts like chairs and doors and some other stuff, but keeping the strength and stiffness same or maybe more. So the 3D printing gives them advantage of yeah, optimize designs and do the simulation and and to get the reduction of weight, and same time the maximize the strength of the parts. So some parts also used for film props, like this Aston Martin DB5, which was printed for the movie, James Bond movie Skyfall. So we printed three pieces of this car, and the scale we use is 1:3. So 1/3 of scale we use than the original. So they scan the original Aston Martin car, and then the CAD data, with the CAD data we printed the parts for the film, and they used in the film. Uh, the the finishing was so good, like, you know, in a close-up looks it's also very difficult to make out the difference between the original and the printed part. So they printed the body and some other small parts on the uh, on the 3D printing machine from VOXELJET, and they uh, like car manufacturing, they assembled it on a steel structure. So this car in a film, they blew up one car in the film, so they obviously didn't blew up the original Aston Martin car, so they used this prop to blew up. So uh, the lead time for producing this is 5 days, and the build time for build time in 3D printer is just 25 hours, and in 5 days uh, the prototype was ready. Uh, Another case study of sling ball, which is made of sand printing, used for art and design. This sling ball is placed just outside the VOXELJET facility. Uh, so the casting is done with the aluminum. The printed volume was 96 meter cube. They printed almost 23 different pieces. The thickness of the the thickness of the part is 8 of each piece, and they are welded together, and then yeah. So it's really a complex design, and yeah, it's possible with the 3D printing. Uh, Also, sand printing can be used for the concrete casting. So we can make a formwork with the sand printed parts. Uh, so uh, this uh, formwork for sand from the sand casting is manufactured for the nest, and the weight of this the total area of the ceiling was 80 meters square, and yeah, it can be used for the concrete structure also, for different shapes. And so
Is it over?
yeah, so this is the last slide, I think. So 3D printing can be used for the concrete, different to manufacture the different concrete shapes also, and also for the art and architecture. You can see on the right side the pictures of very complex art designs are produced with the 3D printing and then coated with the paint, and those are kept in the exhibitions. So this is what the 3D printing can do, and it can be used for industrial purposes also and for the production. Yeah. So
Okay, thank you very much. The students can ask questions if there are any. So this was a wonderful session on particularly the domain of printing the cores of castings and also the complete mold as well. So these are the special processes mentioned, like investment casting, that is a special process. So if you have, the participants have any questions, they can ask. You can also type in the chat box, or you can also speak directly. So in the when we use sand as the raw material into the 3D printer,
yeah,
so basically because sand is essentially silica,
yeah.
uh, so essentially we are just melting the binder only. Is it like that?
No, sand is the base material, and there is a binder which is which we use for the mold making, like for gluing of the parts. So the
Yeah, yeah.
printed jets the binder on the sand, and basically sand also have kind of hardening material in it, so that when we jet the binder, the chemical reaction takes place, and at the room temperature, the bonding happens, and then uh, yeah, it you get the part.
Okay. Okay, I think there are not any questions from students, because probably these terminologies may be new for some students, particularly the investment casting and these terminology. But definitely they can have a look at the company's website later on. They can read about the process in more detail,
Yeah,
and they will understand more.
yeah. There
So thank you, Sachin. Thanks. Yes.
there are a lot of case studies on the on our website also for the different customers, and also there are a lot of videos also,
Okay.
so they can go through these videos so that they can have an idea, different applications and how the process works. And yeah, if they have any questions also, like they can contact me on my email.
Okay. Okay. Thank you, Sachin. Thank you for this wonderful session. So you may leave this session. So we will just continue for some few more minutes. So thank you very much.
Yeah, thank you, sir.
Thank you.
अच्छा, ये तो share.
Okay, Naseem, do you want to take over? Naseem.
हेलो सर, आवाज आ रही मेरी?
हाँ हाँ, आ रही है।
हाँ सर, तो मैं कंटिन्यू कर सकता हूँ। तो ब्रेक देना है सर बीच में, कंटिन्यू करना है फुल फ्लैश?
हाँ, तो तुम थोड़ी देर के लिए अभी कंटिन्यू कर लो, देन फिर ब्रेक कर देंगे। ब्रेक के बाद भी, क्योंकि तुम्हारा सेशन आज ब्रेक के बाद वैसे रखा हुआ है, बट यू कैन स्टार्ट नाउ फॉर मे बी 20 minutes or so, 20-25 minutes.
ठीक है सर, मैं एक सेकंड। हेलो हेलो, आवाज आ रही है सर मेरी?
आ रही है नसीम सर, आ रही है।
मैं कंटिन्यू करता हूँ। बोलो सर, आपको याद है कुछ में लास्ट लेक्चर में जब प्रॉब्लम आई थी कनेक्शन की, तो कहाँ तक कवर हो गया था?
उधर शुरू स्टार्टिंग कर दो नसीम सर, उस वाले से पहले से स्टार्ट कर दो आप।
पीपीटी विजिबल है बोलो सर?
हाँ विजुअल सर, विजुअल।
So I have covered approximate metal matrix composites and application of metal matrix composite, and I have also explained structural property, XRD and SAM, and similarly I have covered SAM part, EDS part. Now this is the application of metal matrix composite. I have also covered this portion. This is also another application I have covered, and I have also covered this portion, carbon fiber reinforced plastic application of in Boeing 787, and also the figure 2 is also cover assistant access door, and these are the sports goods, space application, and this is the research journal, funding approach, lay woods, and lay ceramics. In carbon fiber reinforced plastic, we used a carbon fibers as a matrix and a reinforcement. Sorry, carbon fiber as a reinforcement and plastic as a matrix. So combine both these things, plastic and fibers of carbon, we prepare a carbon fiber reinforced plastic. Now second one is labrix. Labrix is a 3D printing material that give parts the look and feel of gray stone while retaining the resiliency of plastic, making it ideal for landscape and architectural design. Next one is Lewood's D3. Lewood's D3 is a wood-like 3D printer material that gives 3D printed object the look and feel of fiberboard. It also imbues parts with other wood-like attributes, such as the ability to be cut, painted, and sanded. Lewood's D3 is made from a combination of recycled wood particles. Now, last one is Les Ceramics. Les Ceramics filament is exactly what it sounds like, a clay engineer for 3D printers that can be used to make ceramics objects. Les Ceramic has all the capabilities of normal clay, including the ability to be fired to give it a nice glossy look and increase strength. This is the carbon fiber reinforced plastic के layout, simple layout है ये. इसमें आप देख रहे हो यहाँ पे ये जो black wires आपको दिख रहा है fibers. This is the continuous carbon fibers. And another is the plastic filaments that is called thermoplastic, and when both these is combined in this portion that is called nozzle, and this is the heater. और जो डायमीटर की यहाँ पे रिक्वायरमेंट होगी उस डायमीटर का वेरिएशन या वी कैन डिक्रीज और इंक्रीज द डायमीटर ऑफ द फाइबर्स विद द हेल्प ऑफ नोजल. दिस इज द नोजल व्हिच कंबाइन both fibers, filaments and thermoplastics and carbon fibers, then combined and we prepare this carbon fibers reinforced PLA. So here we see यहाँ पे केस जूम करके देखो दिखाया गया है थोड़ा इसके जो फाइबर्स हैं उनको. यहाँ पे आप अगर नोटिस करोगे तो यहाँ पे स्पॉट्स बने हुए हैं ब्लैक एंड वाइट. जो वाइट वाला पोर्शन है वो यहाँ पे रिप्रेजेंट कर रहा है आपके कार्बन फाइबर को, और जो आपका वाइट वाला पोर्शन है वो रिप्रेजेंट कर रहा है थर्मोप्लास्टिक फिलामेंट्स को. सो इस तरह से फाइबर्स जो प्रिपेयर हो जाता है. ठीक है. नाउ मैं नेक्स्ट स्लाइड पे जाने से पहले आई वांट टू शेयर सम वीडियोस, जिस वीडियो में आपको ये दिखाया जाएगा कि जो फिलामेंट्स है वो कैसे प्रिपेयर करा जाता है, उसका जो बंडल होता है वो कैसे तैयार होता है. सो मैं आपके साथ कुछ वीडियो शेयर करूँगा. देन आफ्टर दैट वी गो थ्रू एप्लीकेशन ऑफ कार्बन फाइबर्स. And which is used in 3D printing. So here you see, this is the paste, cellular composite का paste है. वो ये जैसे आपका needles होता है ना, then उसमें fill करके then you can put on the papers like this. तो यहाँ पे 3D printer है, उसमें paste insert करा गया है और उसका यूज करा गया है for making a particular object. सो जो भी डिज़ाइनिंग है खैर वो तो प्रोग्रामिंग पर डिपेंड करती है. जैसे ही आप प्रोग्रामिंग करोगे वैसे डिज़ाइनिंग आपको मिल जाएगी एंड उस टाइप का सैंपल आपका प्रिपेयर हो जाएगा. आपके जो फिलामेंट है वो एक तरह से पेस्ट है, नॉट ए हार्ड वायर. वो सिंपल पेस्ट प्रिपेयर करा गया और उस पेस्ट की हेल्प से यहाँ पे आपका मटेरियल बना. लाइक जैसे कंस्ट्रक्शन होता है और आप कंस्ट्रक्शन में आप देखते हो वॉल वगैरह आपकी प्रिपेयर होती है, तो जो भी आपका सीमेंट कंक्रीट से स्लैरी प्रिपेयर होती है उसकी हेल्प से वॉल बनती है, तो पेस्ट बन जाता हो पहले से ही. सेम ऐसे यहाँ पे भी पेस्ट है, अब वो 3D प्रिंटर के थ्रू प्रोग्रामिंग के थ्रू यूज हो रहा है और आपका जो ऑब्जेक्ट है वो प्रिपेयर हो रहा है. सो दिस इज ए टेक्निक which is used in a 3D printer for a composite material. And here the composite materials, cellulose composites. Now, after this video, I want to share a video which prepare the filaments. This is the cellulose composites. Now, I have shared again.
My name is Joshua Smith. I'm with MakerGeeks.com, and we sell 3D printers, 3D printer filament, and do manufacturing here in Springfield, Missouri. Well, I started manufacturing our own filament. There wasn't a
Yes. हाँ जी
quality control issue. There wasn't really even a price point issue. It was just the fact that we were buying everything that we were getting from China, as is everyone else in the world, and we thought we could do it ourselves. So making filament step by step is you start with a raw resin, PLA, ABS, whatever it is. It's usually granulated. The resin is always either clear or white. It doesn't come colored. You put it into a blender if you're going to mix a pigment or an additive with it. The additive could be anything from like a structural integrity type additive that might give it more strength or impact resistance, to magnetic properties or just color. So if you want blue, you add blue pigment to the resin. Turn the blender on, it blends, and now you have blue resin. So from there it goes into a drying process, usually about a 2-hour dry at anywhere from 60 Celsius to 80 Celsius. This is really important. It's kind of the one part that you can skip if you're trying to make filament really quickly. And I think that's why people get filament that pops on them or jams on them. It's because they didn't take the time to dry it. Then it goes into a single screw extruder, which is probably one of the most common manufacturing tools in the world. So once it comes out of the single screw extruder, which is where it's heated and mixed and extruded into a solid monofilament, then it goes into a warm or hot water tank, which gently cools it, and that's how you get round filament. If you ever have oval filament, the reason you have oval filament is because they had their water temperature at the wrong temperature for whatever they were running. So if you have your hot water temperature set right and your nozzle temperature set right and the resin is set right at the right temperatures, you come out with perfectly round filament. So from there it goes into a cold water tank and it runs through that for maybe 20 or 30 feet, and then it starts getting wound and put onto a spool. So the way that you get either the 1.75 or the 3 mil or the 2.85, and I thought this was interesting because I thought it would be a different die that would come out at a different size. And it's actually not. It's a tractor system, and it pulls that filament out of the extruder nozzle at a constant pressure. And so if you want 1.75, you pull faster. If you want 2.85, you pull slower. And of course, that's going to make that filament smaller or bigger. So how you control the tractor system is how the diameter comes off the machine. So if you have a consistent diameter, then you know you have your process right. And we have a laser gauge that it goes through in real time that monitors that. So if I start seeing that jump up and jump around, I can pull the filament off, and fix whatever the problem is. But as long as that's running, right on, you know that your process is right. And then we print with what we do. We print probably upwards of 100,000 hours a year on our machines, and we still print probably 30 to 40,000 actual printing hours every year, and we only use our filament. So if there's a problem, we're going to find it. So this is another reason we kind of know we're the only ones that are doing it. This is a major manufacturer of these extruders, and they couldn't get visas to come over. So nobody came to train. So it shows up. It takes up that whole space. So I put it together. I assembled it, wired it. It's an odd thing to Google this because it's like this void of information because people are doing it. It's just like people build jet engines. But Boeing doesn't blog about it. Well, people are doing this in China, but they're doing it on, $100 million levels. They don't blog about it. So it's like that thing you got to figure out. And it really is the temperature of, there's 4 zones in the extruder. Each zone has to be the exact right temperature in those 4 zones in the right sequence for the speed and the traction speed. And then each water tank has to be exact. It's that precise. And it has just been like this constant battle of like prayer, and then you get an answer, and then you go back and you change something, and then you're sitting at home and it's like, oh yeah, That's the answer. You go back and try it. It will be science. There will be a time when it is like desktop printing, where you push the button and it's always that number. But for right now, it truly is that. It's an art form, and you've got to be able to kind of flex with that.
Okay, now another video which is 3D printing with the help of carbon fiber.
This roll of ColorFab XT CF20 has been sitting untouched in my shelf for over a year now. Now, I finally found the time to put this carbon fiber filled material through its paces. This week, we'll be looking at print quality, mechanical strength, and temperature performance of this more exotic material, and I'll also talk about some safety concerns. Guten Tag, everybody, and welcome to CNC Kitchen. ColorFab XT CF20 comes nicely sealed on 750 gram spools that sell for $50, which gives it a price of $67 a kilogram. This filament is based on ColorFab's XT material, which is copolyester based and filled with 20% carbon fibers. The carbon is added as short fibers, which during the printing process orientate themselves in the print direction, which gives the part very unique properties on which I'll come later. When printing this kind of filled materials, it's very important to use abrasion-resistant nozzles, because otherwise the inside of your hot end will erode away in no time. I used a hardened steel 0.4mm nozzle from E3D, which is capable of handling this task. Tungsten or ruby nozzles are also an option, but never ever print reinforced filaments with brass or stainless steel nozzles. Usually I print my whole set of test samples and then analyze them. Unfortunately, I noticed after the first run that the printed parts showed quite a lot of porosity, probably due to moisture, so I dried the roll of filament in my oven at 65 degrees Celsius for around 6 hours and reprinted all of the material test samples, and this filament test ended up to be way more effort than I anticipated. The first thing I noticed was that instead of an extrusion factor of 100%, I now needed to increase it significantly to 113% to get good prints. I printed all of the parts as always on my original Prusa Mark IIs, where I added some magic glue on the 70-degree bed and didn't have any warping or first layer adhesion problems as soon as the first layer thickness was set correctly. I tried fan speeds between 0 and 100%, where starting at 25%, the overhanging parts of the prints looked very nice. In the end, I settled with 35% fan for the rest of the samples. I tried nozzle temperatures between 230 and 270 degrees Celsius, which all of them worked fine, though 250 degrees looked the best and had proper layer adhesion, so this was the temperature I used for the rest of the samples. Since the material is a copolyester, I had some issues with bits of material sticking to the nozzle and the heat block, which let loose from time to time and ended up on my parts. Overhangs printed great up to 65 degrees, and boy, look at these outer surfaces. The matte look gives these parts a finish I haven't seen so far with any other material. The material doesn't string, but left some nasty material blobs at the stringing test, though fine details came out well. Playing around with retraction settings and using dried material would probably increase the quality. Bridging was strange, because at first the part looked really awful. Out of curiosity, I used Slicer Prusa Edition instead of Simplify 3D, which made such a difference. Almost perfect bridging, even at the largest gap. I tried to tune the settings in Simplify 3D, but nothing I did improved the print quality, which is really strange. The 3D Benchy reflects these results because it showed the blobs at the retraction points and some material bits at a couple of places. Still, if you overlook these, then the rest of the boat looks stunning with the matte black finish. Let's now take a look at the material properties of ColorFab XT CF20. The tensile strength of around 45 megapascals before drying it wasn't very impressive and even lower than regular unfilled PET. After drying the material, it improved more than 20% and ended up with 55 megapascals, which is better but still below regular. Layer adhesion was only okay, and the specimens printed standing failed at 18 megapascals, which is only 1/3 of the strength of the lying fabric. The tensile modulus, so the stiffness of the material, is what really stands out because with almost 3000 megapascals, it is the most rigid material I printed so far. This is the first time when I also tested the stiffness perpendicular to the printing direction, so the upright specimens. If we take a look at a microscope shot of the material, we see that the carbon fibers orientate themselves in the printing direction, and these fibers give the material its superb rigidity. Perpendicular to the printing direction, they are only barely adding strength and stiffness, which is verified by my second test that showed a tensile modulus of only 1100 megapascals in this direction. So keep this in mind with your designs. If you use fiber-reinforced materials, they have very different properties in and perpendicular to the printing direction. The filament test also confirmed the superior stiffness of this material, even in comparison to PLA. The slope at the beginning of the test indicates the modulus. The steeper it is, the more rigid a material is. My test hooks failed at around 50 kilograms of load, which is in the mid-range. The standing one only was able to bear 16 kilograms until failure, which confirms the previous tests. Temperature resistance was good and the material stayed rigid up to 80 degrees and then totally failed at 85 degrees Celsius. The impact strength was okay and an improvement over regular PETG or PLA, but far away from the toughness of, for example, polycarbonate. I've been mentioning safety concerns in the beginning. This material is filled with lots of very tiny fibers, which might come loose during printing, cleaning, or reworking. I wasn't really feeling comfortable printing XTCF20 in my office, and when reworking this material, which by the way works very well, a respirator is definitely a must. I don't know if I'm overcautious, but I have a bad feeling having these particles in my office. What do you guys think? All in all, it was very interesting for me to work with ColorFab's XT-CF20. It requires some special setup due to the special nozzles needed, but delivers stunning looking parts. Overall, strength was only okay, but the stiffness of the material is really standing out. If you need a material that is different than most other materials, this is definitely not a bad choice. If you require only strength and toughness, there are other materials around that might be more suitable. You can find links to the material and the test methods I used down in the description. The detailed test report, together with the printing profile and all of the test samples, are available for my Patreons. If you enjoyed this video and learned something, then hit the like button and subscribe to the channel for more.
So now जो हम डिस्कस कर रहे थे पावर पीपीटी अपनी, उसमें मैं आपको so here तो यहाँ पे देखिए, यहाँ पे फॉर टेंसाइल टेस्टिंग 3 सैंपल्स हैं जो प्रिपेयर करे गए हैं उनकी स्ट्रेंथ चेक करने के लिए। सो पहला आपका PLA है जो प्रिपेयर करा गया है। सेकंड वन इज कार्बन फाइबर एनफोर्स्ड प्लास्टिक मटेरियल है। नाउ थर्ड वन इज JFRP, तो जूट फाइबर एनफोर्स्ड प्लास्टिक। दिस इज द जूट फाइबर एनफोर्स्ड प्लास्टिक। सो यहाँ पे 3 सैंपल प्रिपेयर करे, तीनों पे टेस्टिंग की गई। तो यहाँ पे देखिए आप ग्राफ, यहाँ पे पहला है आपका टेंसाइल मॉडुलस का और नाउ सेकंड वन इज फॉर टेंसाइल स्ट्रेंथ का। इन टेंसाइल मॉडुलस वी सी कार्बन फाइबर रिइंफोर्स्ड प्लास्टिक की जो टेंसाइल मॉडुलस स्ट्रेंथ है वो 6 टाइम इंक्रीज कर जाती है एज कंपेयर टू PLA। सो और इधर आप राइट में देखेंगे टेंसाइल स्ट्रेंथ फॉर कार्बन फाइबर रिइंफोर्स्ड प्लास्टिक इट इज आल्सो 4.3 टाइम्स फ्रॉम PLA। सो कार्बन फाइबर रिइंफोर्स्ड प्लास्टिक की जो स्ट्रेंथ है, मे बी इन केस ऑफ टेंसाइल स्ट्रेंथ, मे बी इन केस ऑफ टेंसाइल मॉडुलस, इन बोथ द केसेस इसकी जो स्ट्रेंथ है वो PLA और GFRP से बहुत ज़्यादा होती है। और इवन कभी कभी जो हमारे बेस मटेरियल्स होते हैं उनसे भी इसकी स्ट्रेंथ ज़्यादा होती है। सो नाउ आई वांट टू डिस्कस द एप्लीकेशन ऑफ कंपोजिट मटेरियल्स। Okay, now start discussion about application of composite materials. So these are the composite materials which have various application, like carbon fiber and its application, fiberglass and its application, fiber reinforced concrete and its application, laminated floors, blood-proof glasses, modern light armors, aerospace application, construction application. So in carbon fiber, as this is the carbon fiber reinforced polymer or maybe reinforced plastics. So here we see जो ब्लू कलर में आपको दिखाई दे रहे हैं, that is called as fibers. जो येलो कलर में है वो है आपके कहलाते हैं मैट्रिक्स. सो इन केस ऑफ कार्बन फाइबर रेनफोर्स प्लास्टिक विच इज मैट्रिक्स और विच इज रेनफोर्समेंट. और मैं आपसे पहले डिस्कस कर चुका हूँ कि जो बेस मटेरियल हमारा होता है उसको मैट्रिक्स बोलते हैं, और उसके अंदर जो सेकंड या थर्ड वन मटेरियल हम इंसर्ट करते हैं दैट इज कॉल्ड एज फाइबर. सो कार्बन फाइबर रेनफोर्स प्लास्टिक में क्या होगा, जो मैट्रिक्स होगी वो आपका होगा इपॉक्सी, पॉलिस्टर, विनाइल एस्टर, नायलॉन. ये सब क्या होंगे हमारे, ये मैट्रिक्स होंगे. ठीक है, और ये आपके हार्ड फॉर्म में भी हो सकते हैं या आपके लिक्विड फॉर्म में. इपॉक्सी वगैरह आपकी लिक्विड फॉर्म में भी हो सकती है, ऐसा कोई जरूरी नहीं है कि वो सॉलिड मटेरियल हो, वो लिक्विड फॉर्म में भी आपको हो सकता है. जैसे इपॉक्सी और हार्डनर वगैरह जो आते हैं वो इन लिक्विड फॉर्म में ही होते हैं बेसिकली. सो यहाँ पे कोई ऐसा क्राइटेरिया फिक्स नहीं है कि वो लिक्विड हो कि हार्ड हो. सो दिस इज द मैट्रिक्स. नाउ सेकंड वन इज रीइंफोर्समेंट. तो रीइंफोर्समेंट में हमारे क्या क्या हो सकते हैं, कार्बन फाइबर्स भी हो सकता है, रैबिट्स भी हो सकते हैं, एल्यूमिनियम भी हो सकता है, और अल्ट्रा हाई मॉलिक्यूलर वेट पॉलीथीन हो सकती है, जैसे यहाँ पे डायग्राम में दिखाई गई फाइबर्स को. दीज आर द रीइंफोर्समेंट. सो इनको मिक्स करा जाएगा और इनकी हेल्प से मटेरियल को प्रिपेयर करा जाएगा. सो द एप्लीकेशन ऑफ कार्बन फाइबर रेनफोर्स्ड इज साइकिल फ्रेम, वी ऑलरेडी डिस्कस. हॉकी एंड द टेनिस रैकेट्स का जो फ्रेम है वो भी इसी का बना होता है, क्योंकि एक्चुअली जो कार्बन फाइबर होता है ना उसका जो वेट होता है वो बहुत कम होता है. सो डेंसिटी लो होती है मटेरियल्स की, तो हैंडलिंग करने में आसानी होती है, चाहे वो हॉकी हो या आपका रैकेट्स हो. इवन अगर आप थोड़ा रिव्यू करके देखोगे तो जो हमारा बैट होता है ना, क्रिकेट बैट के पीछे भी कार्बन फाइबर की सीट से रैप करा गया था. अगर आप थोड़ा गूगल करोगे तो आपको मिलेगा. इवन उस पर थोड़ा इशू भी आया था एक दो बार. जो रिकी पॉन्टिंग था उसने भी वो वाला यूज किया था, उस बैट को यूज किया था क्रिकेट में, कार्बन फाइबर से लैमिनेशन टाइप की करके बैट्स पे. सो दिस इज द अनदर एप्लीकेशन ऑफ कार्बन फाइबर इन एरोस्पेस. जो हमारे फ्लाइट वगैरह जो मैं लास्ट टाइम भी डिस्कस कर चुका था कि 50% कंपोजिट मटेरियल यूज हो रहा है इन फ्लाइट्स आल्सो. Now another category is fiberglass. In fiberglass, the base material means matrix is also same, which is used in carbon fiber and for plastic, epoxy, polyester, vinyl ester, and nylon. And here is the reinforcement is glass fibers. और जो किससे बना होगा, या तो सिलिका से बना होगा, या ऑक्साइड ऑफ कैल्शियम से बना होगा, मैग्नीशियम से, बोरोन से, किसी से बना हो सकता है ग्लास. तो ग्लास यूज एज ए फाइबर्स एंड एज ए reinforcement. And base material, or we can say the matrix, is polysters, nylons, resins, hardeners, etc. So the application of fiberglass is storage tank. तो जितने भी टैंक होती है हमारे ऑयल स्टोरेज करने वाले, गैस स्टोरेज करने वाले, वहाँ पे हम उस टैंक को हम फाइबर ग्लास का बने होते हैं वो यूज कर सकते हैं. इसके अलावा जो बाथ टब होती है दैट इज आल्सो मेड ऑफ फाइबर ग्लास. एंड दिस इज द पाइपिंग सिस्टम. सो जो भी पाइपलाइन वगैरह अगर हम यूज करेंगे तो वहाँ पे भी फाइबर ग्लास का यूज कर लेते हैं. एंड जो स्पोर्ट्स में आपके हेलमेट्स हैं वो भी यूज होते हैं फाइबर ग्लास के. इसके बाद लैमिनेट फ्लोर, अगर हम फ्लोर वगैरह पे कारपेट वगैरह यूज करते हैं, बिछाते हैं कारपेट, सो वहाँ पे भी हम इसका ही फ्लोर बना सकते हैं, लाइक दिस लैमिनेटेड फ्लोर और हार्डवुड फ्लोर. देयर इज आल्सो दिस इज द बुलेट प्रूफ ग्लास. अगर आप सिंगल ग्लास होगा तो आसानी से ब्रेक हो जाएगा. उन्हीं नंबर ऑफ ग्लासेस आप बढ़ा दीजिए और उनके बीच में रैपिंग कर दीजिए किसी अनदर मटेरियल की. जैसे यहाँ पे आप देख रहे हो जो ग्लासेस है और उसके बीच में जो इंसर्ट कराएगा रेड कलर में, दैट इज कॉल्ड पॉलीकार्बोनेट्स. तो जब पॉलीकार्बोनेट इसके बीच इंसर्ट कर दोगे तो ये आपका बुलेट प्रूफ की तरह वर्क करेगा. जैसे हम देखते हैं ना कार वगैरह में कि बुलेट प्रूफ ग्लासेस हैं. सो बेसिकली इस टाइप के ग्लासेस जो ग्लासेस होते हैं उसमें नंबर ऑफ लेयर्स इंक्रीज कर देते हैं. सो दैट इज सेम एज ए कंपोजिट मटेरियल. सो एक ग्लास की लाइन लगाई, देन फिर अनदर मटेरियल हमने यूज कर, लाइक जैसे पॉलीकार्बोनेट यूज कर लिया, फिर ग्लास, फिर पॉलीकार्बोनेट. तो जितनी नंबर ऑफ लेयर्स हम इंक्रीज करेंगे उतनी ही ज़्यादा उस गिलास की स्ट्रेंथ बढ़ती चली जाएगी. तो जो हम बात कर रहे हैं कि दिस इज वर्क एज ए बुलेट प्रूफ, सो तो उसको हम यूज कर सकते हैं. नाउ नेक्स्ट वन इज दिस वन, यहाँ पे देखिए आप, जैसे सिंगल ग्लास है तो आसानी से ब्रेक हो जाएगा, बट अगर हमने कंपोजिट मटेरियल प्रिपेयर करा लाइक ग्लास फाइबर से, सो वो इतनी आसानी से ब्रेक नहीं होगा। अगर वो फर्स्ट फ्रंट का भी ग्लास ब्रेक कर लेता है तो उसके बाद नंबर ऑफ लेयर्स हैं तो वो इतनी आसानी से ब्रेक नहीं होंगी। ब्लड प्रूफ की तरह काम करता है। जो ब्लड प्रूफ हमारी जैकेट होती है वो भी प्रिपेयर होती है। उसका मटेरियल, द ब्लड प्रूफ वेस्ट कंसिस्ट ऑफ ए पैनल, ए वेस्ट सेफ शीट्स ऑफ एडवांस प्लास्टिक पॉलीमर that is composed of many layers of either Kevlar, Spectra or Steel. That is the material which insert the layer of woven Kevlar are sewed together using Kevlar thread, and while the non-woven Spectra shield is coated and bounded with resin such as proton. Now another is army application, bloodproof vest. This is the procedure for prepare the bloodproof vest. So you can study to make a Kevlar, the polymer polyparaphenylene tetraflaminate. This is the material which is used. Must first be produced in the laboratory. This is done through a process known as the polymerization. तो पहला प्रोसेस क्या होगा इसका प्रिपेयर करने का? polymerization. Now next one is the crystalline liquid polymer in the shape of what is then extrude through the spinner. So you can read out. This is the procedure for prepare the bloodproof vest. And now this is the another army applications. This is the aerospace applications, which is also made by composite materials. And this is the dimension. Now another materials which is used. This is the cablers, simply super strong plastics. And this is the advantage and disadvantage. Advantage, maintain its strength resilience down to cryogenic temperature. तो इसका जो temperature वो -196 सेंटीग्रेड तक जा सकता है। हाई टेंसाइल स्ट्रेंथ तो वेट रेशो होता है, मतलब वेट इसका कम से कम हो सकता है बट स्ट्रेंथ इसकी ज़्यादा होती है। और स्टील से 5 टाइम्स स्ट्रॉन्ग होता है। और अगर कोई डिफरेंट केमिकल अटैक है उसको भी रजिस्ट कर सकता है। इवन जो कोरोजन का इशू आता है वो भी प्रॉब्लम नहीं होगी। और डिसएडवांटेज ये है इसका कि इसकी जो कंप्रेसिव स्ट्रेंथ है वो बहुत कम होती है। सो नाउ अनदर इज FRC, फाइबर रिइंफोर्स्ड कंक्रीट। तो कंक्रीट में रिइंफोर्स हमारी ग्लास फाइबर, स्टील या पॉलीमर फाइबर्स होते हैं, इसको इंसर्ट करा जाता है। और दिस इज द, आपने देखा वो जो वॉल प्रिपेयर होती है, दिस इज द डायग्राम रिलेटेड टू कंस्ट्रक्शंस। So I think this is time for lunch break, 11:40. Okay, so this is the time for lunch break. ये lunch break का टाइम हो गया है तो हम लोग अभी ब्रेक लेते हैं, तो फिर हम आते हैं वापस 12 बजे मिलते हैं। तो थोड़ा और है इसमें, वो मैं आपसे डिस्कस करने के बाद उसके बाद हम लोग क्विज डिस्कस करेंगे। सो कंपोजिट मटेरियल पे मैंने कुछ क्विज बनाई है और आसान क्वेश्चन है, इतना टफ नहीं है, बेसिक सर। आई थिंक मैक्सिमम को उसके आंसर आते ही होंगे। सो हम क्विज डिस्कस करेंगे फिर 12 के बाद। थोड़े 1-2 एप्लीकेशन और हैं, उनको डिस्कस करने के बाद देन वी कैन मूव क्विज। ओके, सो यू कैन लीव एंड वी विल मीट एट 12 PM. ओके, थैंक यू एवरीवन।